I hope that by the beginning of this course you already had some experience with vector or matrix operations in the course of linear algebra or at school, but in case you don't, here is a quick summary of what matrices are. For example, here is a simple system of linear equations. We have 3 equations and 3 unknowns. And in the course of school mathematics, you know that you can apply a simple method of exclusion of one variable at a time to get this matrix into triangular form, where you will have the last equation having 0 coefficients in front of x and y, and 1 coefficient in front of that, and some right-hand side for that equation, and then you will get value for z. Then you will back substitute it into the second equation, and then you will get value for y, and then you will also substitute both into the first one and get the value for x. This is called linear algebra and system of linear equations. This method that I have just described is convenient for simple problems, but not exactly useful when you are going to solve very large linear algebra problems. And in order to help with that, mathematicians came up with notation that simplifies this equation. So this notation is called matrix form of a linear equation. Here we do the following. So first of all, we redefine our x, y, and z as components of a vector. So we say that our x equals to x0, and then y equals to x1, and z is equals to x2. And x becomes our new variable, our new unknown. Second, we write down all our variables in this form. So we take a list, and then we write down all the coefficients sequentially, and then we do the same for the second line and for the third line, and then we wrap this into another larger list. This is now list of lists, or a matrix. This is a third order matrix because it has size of 3 by 3 and all elements are present. And let's call this matrix A. Then on the right side we have 5, 7 and minus 20, and this we call B, and we write them down in a similar way, except for the fact that we don't have multiple coefficients, we just have one at a time. So we have 5, 7 and minus 20. And mathematicians rewrite this equation in the form A times x equals B. So now, instead of having individual equations and individual components, we have just one line, and all the coefficients have been grouped up into this, which is a matrix, and this, which is a column vector. Column vector is also a matrix, but it has a special property that it has only one column in this case. There are also row vectors, which have only one row. Now, matrices are convenient not only because it is convenient to write this whole system in this format and stop thinking about how would you name the next unknown in your linear algebra, but also because they allow us to manipulate this data in a more precise and standardized way. There are following operations that are allowed on matrices. So matrices can be added together, and matrices can be multiplied by a constant, or in terms of mathematics, scalar, and matrices can be multiplied by each other. And finally, you can solve matrix equation that has this form. So you can find x as A inverted, let's type it like this, times B. I will not prove right now why solution for this equation is this. That comes from the properties of matrices, and you will study it in mathematics or linear algebra courses, respectively. But today let's talk about the library in Python that enables you to conduct all these calculations inside Python using the matrix notation. The library we are going to work with is called Numpy, and we can install it using this command. In my case, I have already installed it before, and let's import it. Because it is not a standard library, it requires installation before you can import it. To make operations with Numpy shorter, people frequently use this shortcut import numpy as np, and we will follow this. You can also import just Numpy directly and use it like that, but because NP as a shortcut is so frequently used, you should be aware that when you see something np dot something, it is most frequently reference to Numpy library. Okay, how does this library operate? The basic element of this library is Numpy array. This array can represent both matrices and vectors, and vectors can be either row vectors or column vectors, it doesn't really matter. It can also represent more than two-dimensional matrices or data structures. With this command, as you can see, we are creating a vector matrix, a row vector, that has dimensions of 4 by 1, and its data type is set to Numpy float 64. And this is a double precision float, so 64-bit. And as you can see, the result is an array that contains these numbers that were converted to the floating point. Similarly, we can use list of lists to create a two-dimensional matrix. And we use just a simple Python list as input. And the outcome for a matrix sized 4 by 4 looks like this. So we have 4 rows and 4 columns, and this is a square matrix. But this is a direct way of entering matrices, and you don't have to use it. Instead, you can use one of the many convenient generation functions. For example, one convenient generator function for matrices is numpy.zeros that takes shape of the matrix as first argument and data type as second. And shapes means the dimension of matrix in rows and columns. So we have 3 rows and 3 columns. In a similar way, we can define matrix that will be filled by ones. Another convenient generator for matrices is one that produces matrices filled with random numbers. And in this case, we are going to use random numbers that are coming from normal distribution. If you don't know what normal distribution is, it is a most commonly met in the nature distribution of sample data. The values in that distribution typically lean towards the median value, the mean value. In this case, it is specified by this log variable, and they can deviate from that number by small amounts or by large amounts. And the probability is higher for smaller amounts, and it gets smaller and smaller for larger amounts, but even the largest numbers are still possible with this distribution. The probability of you having larger numbers is dependent on the value of scale. The larger is this number, the larger will be the deviation from the mean value. As you can see, we get a bunch of numbers that are close to 0 and whose range varies from -2.36 something up to 2.036 in this case. But we can run this call multiple times, and you can see that this will generate all the time different numbers, and the span, the distance between the minimal and maximal value, will change. Another convenient generator function is np.diagFlat, and this one takes vector matrix as input, and it converts it into a square matrix in which all the values from these vectors are placed on the diagonal and everything else is set to 0, for example. So if you just need to make a diagonal matrix with predefined diagonal values, this function is your way to go. We have been talking so far here about row vectors, but if you want to define a column vector, you can do it in a similar manner. The only difference is that you need to pass a two-dimensional list, so you need to have a list that contains lists, and inner lists will only have one value each. So these represent individual rows, row 1, row 2, row 3, and within the individual row we will have values for columns. In our case, the only value for column here is 0, for this one is 2, and so on. Okay, now we know how to define vector submatrices inside Numpy. Let's use them to compute something. Here are the simple math operations that you can conduct on matrices with Numpy. First, we declare two matrices. One is a matrix 3 by 3 filled with ones, and then another is diagonal matrix with 1, 2, 3 on the main diagonal. And then we start computing some values with them. So first of all, we compute sum, and as you can see, the diagonal values have been added to the ones in every cell. And then we computed difference, and we have 0 in the first where 1 cancelled 1, and then we have -1 and -2 in the two other diagonal elements. And then we have matrix element-wise product, A times B, and obviously zeros multiplied by ones became zeros, and everything else kept their value. Finally, we have dot product of two matrices according to the correct mathematical equations for dot product, and we have element-wise cosine of matrix elements for A. One important thing that you need to know about matrix operations in Numpy is that when you are going to have matrices for which dimensions do not match, you will sometimes trigger dimension propagation. Dimension propagation means that, for example, if you have one operand as matrix that is 3 by 3, and then you add a vector that is 3 by 1 or 1 by 3 to that matrix, and you add a vector that is 3 by 1 or 1 by 3 to that matrix, in such case, your vector will be expanded to match the dimensions of the matrix, so it will be set to 3 by 3. And it will be done by copying either columns or rows depending on the missing dimension. For example, in this case we are trying to operate on two vectors. One is a row vector, so it's 4 by 1, and the other one is a column vector, so it's 1 by 4. And the outcomes of this are as follows. So we defined our row vector and our column vector, and when we tried to add them, we actually expanded this vector by 3 additional columns to the right, and this row with 3 additional rows below. And when we got these two 4 by 4 matrices together, then we ended up with these results. So they are as expected. So the last 10 is a sum of 6 and 4, and 9 is sum of 6 and 3, and so on. And respectively, for subtraction, we get a similar result, and for matrix element-wise product, we get also similar result, where 0 multiplied by all elements of the first column resulted in 0. However, for Numpy dot product of two matrices, we got just a scalar number of 40. And this is also expected because for dot product, there is no reason to expand those two vectors. The dot product is by definition just sum of products of sequentially taken elements from these two vectors. One other important operation that is frequently used in matrix computations and matrix equation solving is inversion of a matrix. As you can see here, for example, in order to solve this equation for x, we will need to first invert matrix A. And to achieve that in numpy.linalg, there is a function inv, and we can use that function to invert any matrix. For example, we can invert this diagonal matrix that has 1, 2, 3, 4, 5 on its main diagonal, and the product of this operation is 1, all 5, 1/3, 1/4, and 1/5. And this is expected mathematical value, and we can check that it is correct by multiplying A by B, because product of matrix and its inverse is identity matrix, and that's what we get. Sometimes, however, you need not only to solve linear equations and do operations with matrices in terms of mathematics, sometimes you want to do some transformation. For example, if you are working with images or photographs. And in such cases, you might need to work with reshaping and dimension shuffling. So let's talk about reshaping. Here's an example. So as you can see, we have first defined a 4 by 4 matrix that contains 16 elements, and we checked its existing shape, that is 4 by 4, so 4 rows and 4 columns. And then we called reshape operation, and we set a new shape to 2 rows and 8 columns. And as you can see, the outcome of this function is exactly a new matrix that has 2 rows and 8 columns in each. And as you can see, the transformation took first row and then second row and glued them together into one large first row. And then similarly it took third row and fourth row and glued them together again. If we were to change the shape into 8 by 2, so 8 rows and 2 columns, we would get the opposite operation. Instead of gluing the rows together, we will split them. So the first row will become 2 rows, 0, 2, and then 4, 6. And then the second row will become third and fourth row, and so on. This is convenient operation, but sometimes you don't want to calculate manually all dimensions. In such cases, you can substitute one of the dimensions with -1. And as you can see, if we reshape this matrix into 8 rows without specifying exactly the amount of columns, the shape for this matrix will be computed automatically based on the amount of elements. So 16 will be divided by 8, and we will get 2 instead of -1. And with this operation, either 1 -1 or -1 1, you can flatten the matrix into a vector. So you will get either a row vector or a column vector. And of course, you don't have to convert a two-dimensional matrix into a two-dimensional matrix. You can convert a two-dimensional matrix into one-dimensional one by just taking all its elements, and you can see example here. Or you can even convert it into a four-dimensional matrix by specifying the dimensions as 2 by 2 by 2 by 2. And in such case, you will get a 2 by 2 matrix that will contain other 2 by 2 matrices as its elements. And each of those matrices will be basically made out of the row of the original matrix.